Alright, the following problem is number 33 on page 209, and we are given mass, radius, where the object is centered, and a instance at which time equals 0, the distance is negative 6.5 in the x direction, and a velocity in the y direction. Interpreting this picture, one can analyze that since it's centered at 0 and it has a radius of negative 6.5, it is connected. So the object is going to move in a circular motion, and it also states that it's at a constant speed. So the first question I was asking was the direction of vector p, which would be the direction of the ball moving. So to calculate this, you just use p equals m times v, or p, and the only distance that would really change is in the y direction, which is denoted by a according to their diagram. This makes sense because the only force, or the only vector velocity acting is in the y direction. So momentum would only be changing in the y direction, since all other velocities besides y direction are 0. The next question I was asking was the magnitude and direction of the parallel component. Well, because in this instance there's a constant speed, therefore the speed and the magnitude are constant, and it would just be 0. Since it is a vector, it would be the 0 is denoted by a vector symbol. So that was pretty straightforward. Then C was asking what was the perpendicular component and the magnitude. For this one, you can use mv squared over r. This only works when there's a smooth circle, and for this to be valid, it has to be constant speed, and has to be for smooth circles only. And it's also a good idea to understand that this compartment, or this equation right here, the direction is directed towards the center. So after plugging in, you get 492 kilograms per meters per second squared, and the units do come out to be the units for p. For D, it was asking the direction of the net force. So the direction of the net force, the way I interpreted this was, since momentum is only increasing in the positive direction, so it's going to go from quadrant 2 to quadrant 1 to quadrant 4 to quadrant 3. So I assumed that the direction of the net force would be in the positive x direction. For question E, it was asking the vector notation of f net. Since we have both direction and the magnitude, which we solved in the previous problem for C, we simply just have to multiply using the dot product. So it'd be f magnitude times f hat. F hat represents 1, 0, 0. So f net is actually equal to 492, 0, 0. In the book, they had f hat as 0, 1, 0, which would not make this valid at all. Lastly, for F, they gave a scenario where when t equals 0, there were two forces acting on the ball. We were given one force, but we were not given the second force. So to find this, you can simply just do f net equals f1 plus f2. Keep in mind that we did solve for f net for E, so it's simply f net minus f1 to get f2, which was this one right here. So I believe that's it. Thank you. Also, one last thing. Even though it's constant speed, the velocity is changing. So the way I looked at this in the beginning was I was thinking that velocity wasn't changing, but I came to the realization that velocity it can be broken into two compartments. There's magnitude and direction. The magnitude of the velocity doesn't change, but the direction does change. So, thank you.